Hey class, good morning. This is Mr. Bean here. We're with the B2 Honors Physics class 2021, and we're going to be doing the Lab 24 horizontally launched projectile. This will be exam part one, and this is to be completed in your blue notebook. Now, this will also come with a video verification because X marks the spot, literally. Okay, so theory. Take a quick look here. So let's go ahead and kind of figure out what's going on here. So here we have a cliff here, and we have some projectile right here. Okay, all right, okay, and here it is. Okay, so it's going to be launched with some initial velocity here, and we will call it VO. Okay, okay, initial velocity VO. Okay, all right. Now, when it's launched horizontally here, what is the initial angle theta? Anybody in class? When we launch it horizontally, what's the angle? Zero, yes. It is 0 degrees. Excellent. Now, I'm going to ask the class here, before we start any projectile motion problem, what's the first thing we should always do? We want to find the components? Yes, we want to find the components. So we want to find VOX, and we also want to find VOY. Okay. All right. So VOX is going to be whatever VO is, right, times the cosine of theta. So in this case, what is theta? Zero. Okay. All right. And what is the cosine of zero? One. So therefore, VOX equals VO. They're the same. Okay. Because the cosine of zero is one. Okay. Now make sure we are in degrees, not radians. Okay. Now let's take a look at VOY. Okay, so VOY is going to be VO sine. Okay, I'll post this on Classroom here. So sine of zero. Okay, what is the sine of zero? Zero. So zero times anything is zero. Okay, so it is zero. So here we have VOX is VO, whatever the initial velocity is. And velocity in the y direction initially is going to be 0. So, okay, all right, that's going to be important. Now, we'll go ahead and change colors here, and we'll take a look at this parabolic path. I'll go ahead and use yellow. Okay, so the moment it launches here, it's going to follow this parabolic path, right? Kind of like right here, and it's going to land like right here. Okay, all right, let's go change colors. So it's going to take this path here, and this is literally x. Okay, this is going to be x. Okay, and here, x in the initial position is going to be 0. Right, right. It's going to be 0 here. Okay, so this is x here, right? Okay, so everyone's good so far? Good. All right, so this is being launched horizontally, and so this projectile, is it going with gravity or going against gravity? With. Okay, so for our frame of reference, we'll call this the FOR, the frame of reference. We will have going down to be positive. Okay, going down is positive. If going down is positive, what will the value of G be? Yeah, cool. Positive 9.8 meters, right, per second squared. Okay, all right, because the projectile is going with gravity. Now look at this y position here. Now the x. So let's examine it maybe here, here, and then maybe here. Okay, look at the projectile. Now look at the x. Now we're going to assume there's no air resistance, but in real life, is there going to be air resistance? Okay, okay, so we'll assume that there's not any. Okay, is this vector here going? So this is a vector here. Is this going to change at all in the x direction? Yeah, it should be the same. Yeah, it is not going to change. So this is still VO, VO, and even right here, it's going to be VO. Okay, so this will not change at all throughout the entire journey. Okay. Now, what about the y component? Yeah, right here there is no y component, but like right here, is there like a is it starting to emerge? Okay, should it be the same size here or bigger? Yeah, because it's gaining speed, right? And then probably right here, it's going to be like uh, pretty big, right? So as this goes each moment, so Vy gets bigger each moment. And this over here, I'm going to write this. This should be Vo, right? So Vo, this is Vo. It stays the same throughout the entire journey. Okay. So let's kind of pause here for a minute and kind of reflect on that. All right. So now, so the projectile hits the ground right here. Okay, so this location here, based on our previous experience with projectile motion, we know that the X position, how far away it is from where it launched from, is going to, so this here we can predict. Okay, this is what we're going to try to predict here. It's going to be whatever VOX is, right? Whatever initial velocity is, times now, is it the total time it's in the air or the time going down? Yeah, or it's the well in this case, yeah. Now remember, it's not an entire projectile. It's only, if we launched it from here, it would be the total time. But is it really just the time going down? All right, so we will call this the time going down. Okay, the time going down. Okay, all right. So, okay, so whatever now is this now. If I was to take this ball or the sphere here and drop it straight down, would it be the same time? Yeah, it is the same time. Okay. So the time to go here and the time to go here is the same. All right, so let's okay, we're almost done. Okay, so what measurements do I need to know here? Okay, should I probably measure how high this is here? Okay, so we'll call this maybe delta y to make it easy. Okay, we'll say maybe over here. So we'll call this here delta y. So we actually have to measure delta y from here to here. Okay. Now, since everyone is going to be using the same delta y, we'll go ahead and measure it right now. Let me hit pause and maybe. All right. So we're measuring the delta y right now. Okay, and about 77. Okay, so 0.735 meters will be our initial height from which the uh, Matchbox car drops from. Okay, so we have our delta y. So here's our delta y right here. Okay, make sure this is connected here, delta y. And delta x, where it lands, is what we want to predict. Okay, all right, so in order to do this, so I'll go down here to calculations. Okay, and we'll call this here flight time. Okay, flight time. Okay, all right, so usually we want to use the y equation for flight time. Okay, so we have here delta y, right, is going to equal, here is VOY, and we'll call this time down, right, okay, minus 1/2, right, uh, or actually it's plus, right, because it's plus, yeah, G, we'll call this time down squared. All right. Now remember, see, now we got to plug some values in here. Now, did we measure this already? Yeah, so this was already given to us, right? Trevor in this case measured this for us. Okay, or we'll say some guy or some person measured it. Okay, all right. Now take a look at VOY here. Let's recall VOY is going to be VO, right, times the sine of 0 degrees. Okay, and what's sine of 0? It is 0. So this value here is 0. Okay, all right. So if that's 0, then what happens is that this becomes delta y, right? Okay, equals 1/2, right? G time down squared. Okay. So from here, can we solve for the time down? Okay. All right. So yes, so using our advanced algebra skills, we're going to go ahead and solve for the time going down. So the time going down is going to equal, right? It's going to be the square root, right? Okay. It's going to be 2 times delta y, whatever delta y was, which was given to us, divided by, was it g, right? Okay. So there's our total, there's our flight time. Okay. So this is set, right? Is this going to change based on, so what's the flight time based on? 2 is 2, g is g, is the height. So delta y is set. So that's going to be our flight time in the air. It will not change in this experiment. Okay. Now, so in order to calculate or predict x, we have to know what VO is, right? VO, and we have the time going down. Okay. All right. So this is given to us. So what's the only thing we need to know? VO, right? Initial velocity. Okay. Now, so here's the initial velocity. Okay. Now, my recommendation. Okay. Let's do, I would say at least 3 to 5 trials. 3 to 5 trials. Okay. And here I will help each group that comes through here. Okay. So we're going to have a track here, kind of like this here. And we're going to have this, here's our table here, like this here. Right? Here's our table. And so we're going to have our Matchbox car. Hopefully you launch it from the same place. Now, the Matchbox, to help make sure that we launch it consistently, I would probably use like a popsicle stick here. We'll call this popsicle stick. Okay, popsicle. Okay, why would I want to use a popsicle stick? Maybe, or to just kind of like a gate to open it up. Because if you use your hand, you might give some initial velocity. So we'll use a popsicle stick to help it from the same spot. Okay, you're gonna launch it from the same spot. Okay, now here I'll go ahead and use a different colored pin here. We have a photo gate here. Okay, it's kind of like this, and it has a laser here, photo gate. Okay, and this goes to our computer here. Here's our laptop. Okay, or you know device. We'll call this device here. Okay. All right. So we're going to launch this at least 3 to 5 times, and we're going to get maybe we'll get VO1, VO2, VO3, VO4 maybe, and of course VO5. We did it 5 times. Okay, so I do it 5 times here. What can I do to figure out what the actual velocity is? Yeah, absolutely take the average. So we'll take V here, and maybe we'll put like a little bar here. It means that this is the average value, right? So this here is now going to be the average. So we have the average. Okay, you can do it 3 times, 5 times. I would recommend 5 times. Okay. All right. So then you're going to leave. Okay. Now each trial, somebody's going to catch it because we don't want to. I don't want to use the word cheat, but we don't want to know where it's going to land. We want to predict where it's going to land. So each of the 5 trials will have someone here that's going to catch the car. So someone's going to, as the car flies off here, they're going to catch it. Okay. All right. So you're going to go back and you're going to predict what your X is. X is going to be whatever VO average is times the flight going down. And then when you're ready, okay, when I see this calculation, so Mr. Bean needs to see this calculation, okay, and you're going to place the X here where it's supposed to land, okay, and where we go, there we go. We're going to go ahead and do that now on the table here. So here's this table here, right? Okay. Now, should I make sure? Okay, should I put something here straight up and down to know where to mark my X? Because this is going to be X right here, right? I want to make sure that this isn't too far in or too far out because it has to land on the X. So I have to make sure that do I need maybe 2 or 3 meter sticks maybe to help us make sure this is a vertical position? So make sure I align it. So make sure that XO is truly 0 right here. So when I measure my X, I'm lined up exactly with the edge of the table. Because if you're off by a centimeter, it's going to cause it's going to land differently. Okay, so you want to make sure we do that. Okay, all right. Which brings us to the objective, which I'll go ahead and write here, and then that will conclude our discussion. All right, so we'll call this here objective. Okay. All right, so Ryan, what do you think the objective should be? Yes, yes. So predict where car will land, and hopefully it'll be the X. Okay. All right. Objective: predict where the car will land, and then verify. Okay. Then maybe two, verify with video documentation. All right, and then there should be two here, but we'll say two, right? Uh, well, it changes back to one. Okay, so verify with video documentation. All right, that'll conclude.